All right. Good afternoon. Thank you for coming. I'm Eugene, and I will talk about my project that I have been working on for some time. So, what is the problem? So we have these interpreters and compilers, right? So we know these methods and use them frequently. So interpretation is very so both of these methods are good in their own ways, right? So the interpreters, their main strength is that they are very close to program semantics, right? So if we are implementing a programming language, it has some rules that it is for evaluation of the language, and they are very cleanly expressed as an interpreter, right? And that means that leads to very clean code. So we can explore the interpreter, we can debug it very easily, we can test it, right? But on the other hand, it has some a downside. So by its nature, it has to wrap all of the instructions in some glue code, and that leads to the overhead, right? So how do we deal with that? We write compilers instead, and compilers are awesome. They basically operate in two stages, so they split execution into the compiler stage and the execution stage, right? So the compiler stage now takes only the source program, right? And it produces some kind of target code that takes the rest of the arguments to this program, right? And that's all good, but unfortunately, compilers are also harder to develop and maintain because they require a specific style of coding where we don't talk about the operations, we talk about ways to generate these operations, right? And also they require use of some complex libraries and programming APIs. And no matter how easy a compiler infrastructure makes it to write compilers, it will always be harder than to write an interpreter, right? So we can't pick and choose different components, so different advantages of these approaches. So we have to either pick an interpreter and we get clean code, but slow execution. Or we can pick a compiler and we stuck with the code that is harder to grasp, right? But what if we could pick and choose? So what if we could pick direct translation semantics property, and that would lead to code that is easy to explore, to debug, to extend, but also get the multi-stage execution with the corresponding properties for performance. And luckily, this still exists for quite some time, since the 70s, and it's called partial evaluation. So what is a partial evaluator? It is a program that takes not the program and some of the arguments to that program. And it produces a representation of another program that takes the rest of the arguments. So the arguments are split into two groups, right? The first group is passed to the partial evaluator, and the second group is passed to the program produced by this partial evaluator. And we already see that if we apply it to our interpreter with the source program as one group and arguments as the other group, what we get is pretty close to multi-stage execution that we used a compiler for, right? And all of the analysis were done at this first stage that it takes only the source program, and the compiler stage it doesn't have access to the program, and it doesn't have any analysis and transformation passes. And here we can achieve the same result. We can embed all of the analysis and transformations in the first stage, and the compiler program will be free of these extra overhead layers, right? So, well, first the remark, it requires all the arguments to be separated, right? So if we want to apply this method to any interpreter, we need to specify which arguments go to which stage, okay? And here we say that source program is stage 0, or static, as it's traditionally called, and arguments are in stage 1 or dynamic, right? We have to make some additions to that, some adjustments. So first of all, we don't really want this mix here, so this partial evaluator, because the program here, the source program, is just another argument to our interpreter. And since the main application of this is for JITs, right, the program will be bound at runtime. We don't know it in advance, right? But here, in the above picture, we have to partially evaluate the interpreter every time to reprogram, right? And that adds its own level of interaction and its own interpretation overhead. That is exactly what we want to avoid. So instead, we're going to use a specialized generator in the picture below, right? So here we have this this generator that produces a two-stage program, right? So we can run it at compile time and produce our two-stage specializer that then takes the source program in one stage, the arguments in a second stage, and produces the result, right? Yeah, and also why not generalize to multiple stages, right? And for example, we could have a system where that processes some queries to a database, for example, right? And it can have multiple levels of parameters, right? So in one stage, we can have like prepare statements. So it is a broad description or a plan of a query or of some kind of query or procedure that we want to interpret. And we can already specialize our interpreter with respect to this prepare statement. And then for each query, the parameters that we get like from a system or some component, we can emit code pretty fast, and the resulting code will be specialized to our query. Right? So what we want is we want for our generator to emit a multi-stage program, right? Okay, so let's build it, right? For LLVM, right? So why this is the focus of the project, right? It's kind of truncated here, but this is LLVM, right? So why LLVM? First of all, there are some existing partial evaluators for some languages like C and ML family languages, but they are all kind of forced to implement the same algorithm, essentially. All right, and what is a better place to implement this algorithm than in a language-independent optimizer, right? So let's put it there, right? And that will enable lots of languages. So with little additions to the front ends of these languages, we can take advantage of this common functionality in the optimizer. And what we get is a way to build a multi-stage generator for each of these languages. All right. So the project is an extension to LLVM, right? It has some attributes and intrinsics, and the main part is the two passes. So we have an analysis pass and a transformation pass, right? So first of all, how do we represent annotations? Well, as I said, we have to annotate the program in order to tell the system which arguments go to which stage, right? So we have to. What we want is to split a function into, like, in this case, two functions. One will take y and the other will take x, right? So here we add some attributes to the parameters, right? So we say that x is stage 1. It goes there. The result is also stage 1, and we also have the attribute on the function itself. That may seem redundant, but it's not, because it is natural to wish for the last stage to not take any arguments at all. So, for example, we can have a function at the very last stage that doesn't take any arguments, but instead it accesses some memories, or like it may call some external functions for certain operations, right? For example, it can write to disk or like store in some memory, like compose a string of letters or something like that. Right. What is the interface here? So the intrinsic takes a function pointer and the arguments, right? And it produces the program. And in clan, right? So there is some extension to clan. So we have this attribute on the function, declaration, and the result of this function attribute will be the body for this function. So we don't have a body in the source code, but a client will generate will generate one for us using the intrinsic. Right? And how do we use this? Well, let's say we have some interpreter in C. Right? So we wrote some interpreter for a language, or maybe it's something like an interpreter. Like maybe we match some grammars. So we have some grammar descriptions and a string. Right? So we add the attributes to the arguments to declare which arguments go to which stage. Right? And then we add this function declaration with the mix attribute that references the function, right? And then we need to have some layer that translates the representations of programs into object code. Right? So we can use org for that, and of course we can. So the function will create IR representation of a specializer in some context, and we can manipulate this context. We can create like in our application, either a single context for everything, or multiple contexts for different situations. So it's very flexible in this case. Yeah. So now we'll talk about implementation for a bit. So here we have. So what happens in Clan is that it creates this body using the intrinsic, right? Next. The intrinsic in the optimizer will be replaced, expanded into a function call. So this function is actually like the main power horse. So it takes the stage 0 arguments and it returns another function that takes a stage 1 arguments and so on. Right. So this is actually our specializer. Right. And at the high level, what we want is we want to split a function that takes arguments of various stages into a chain of functions, right? Each function will take arguments of each stage and return the representation of the next function that takes arguments of the next stage and so on, right? So we apply a certain transformation a number of times, and all this transformation does is that it peels off the arguments of the last stage. Right? It removes them from the original function, and it replaces the result with the function or representation of a function that takes these peeled off arguments and returns the old result. Right? Let's go down to IR. So yeah, we have function f here with the arguments x, y, and z. The argument z is in second stage, stage 2. Right, and after one transformation, we get this function g that doesn't have z, but instead it returns a value pointer, right, which is actually a function pointer, right? And this function g creates this new function that takes z, right? And you may also notice this context argument, which is used for accessing the current IR module context and so on. Okay. After the next step, we get this function h that takes all arguments in one stage. So this is one missing argument here. It's x, right? So it doesn't have y anymore. It only has x. Okay, on the level of a basic block. So on the left, we have an example of some control flow in our source program, and on the right is the example basic block of this specializer. So in the example, we have 3 blocks, A, B, and C. Block A is in stage 0, and 2 instructions in stage C, in basic block C, are also in stage 0, right? And everything else is in stage 1, so dynamic. And what we see in the generated code here is that we only have one block for A, because A is the only static block. And we have only 2 instructions that are copied from the source, from the original function. And the rest is replaced with calls to llvm API, right, to recreate this control flow graph. So we have this calls append basic block here that these calls create blocks B and C. And we have some instructions like build binary operations here that creates the add. Yeah, the add in block B. All right, and in general, all static basic blocks are transformed into basic blocks in the specializer. All instructions that are static or of stage less than the current stage are copied as is, essentially, and everything else is replaced with calls to llvm.c API, right, to recreate this at the next stage. Yeah, so with calls, so we would like to support not only one function, but a set of functions, because the interpreters are written as a set of functions typically. Yeah, and what we want is to stage all these functions at once. So first of all, we gather the set of functions that form the interpreter. Then we apply this transformation once. So we lower all the functions at once, and while doing that, we replace the calls with pairs of calls. So the first call will go to the function that is a specializer for this stage. So here we have a call to f.mix here, but this is a generated function that that specializes this function f, right? And it returns a function for the next stages, right? So it only takes x here, and it returns a function that takes y. And so we build calls in the next stage that that call this returned function on the previous stage, right? Yeah, so we have the pair of calls. This is the normal call, and we have a llvm build call here to recreate this call later. So what happens to the control flow graph? So we have some control flow graph at the beginning. It is truncated, but you can see the idea. So we have some basic blocks. So green blocks are of stage 0 here, red blocks of stage 1, and white of stage 2. And what happens after one transformation, we eliminate all white blocks. We fold them into the block A. A1 here, or like C1 here, right? So and on the next stage, we fold all of the red blocks that are left into block A0, right? So block A0 will create these blocks. And actually, what happens is that it won't recreate this graph exactly. It will unfold it, right? It will create the control flow graph from the basic blocks of the corresponding blocks here, right, folded blocks, right? So here we have not the loop, but the unfolded loop with 2 iterations, and on the next in the next stage we get like a similar kind of graph, right? Right. So now we talk about binding time analysis. So we assumed, so the previous section talked about how we separate one function into a chain of functions, right? Now I'm going to talk about how do we know which instructions go into which stage, right? So how do we actually know which instruction built where, or like when, right? And so for basic blocks, right? So this analysis, it provides just that information. So it assigns an unsigned like stage number to every instruction into basic blocks, right? And the way it works is that first of all, it assigns stages to parameters. Like if a parameter is declared with a stage attribute, like all parameters are, right? For this to work, it assigns that number, right? Or if we have an external call that we know nothing about, we can assign it to the last stage, right? And then it runs this minimum fixed point algorithm to propagate the stages to all of the other values in the function, right? And it can reach a contradiction, so it can learn that the annotations are inconsistent, and it will report an error. Or it can find an ambiguity in trying to resolve these errors, and it will report them. Yeah. So here's the example with optanalyze. Yeah, so each instruction gets a stage, and blocks also get a stage. Yeah, and yeah, these are the rules that it tries to satisfy. I won't talk about all of them, but for example, the rule on the rightmost rule at the top says that the stage of an instruction should be the same or greater than the stage of the argument, which makes sense because the instruction that depends on the operand must be executed at least then or later, right? But I want to stop in one rule in particular, right? So this rule states that if we start from some stage number, right, and from any basic block, and we trace the branches from this block, yeah. So we should have exactly one terminator that we can reach through terminators of greater stages, so of all dynamic stages, right? Yeah. So here on the left we have an example. We have basic block A, right? And there is only one terminator that is reachable from block A on terminators of stage 1, right? So if we traverse the graph as starting from block A and going on all edges with a stage 1 or greater, then we reach exactly one terminator. It's in block C. And this terminator goes right here, so it is a terminator of the specializer, right? If we had two, we couldn't build this specializer this way. Yeah, and we can prove termination. So if the resource program terminates, then the specializer also terminates. And this is it's very easy to remove some of the rules and to get to the situation where we have a specializer that doesn't terminate, but the source program did, right? And that would be a problem. Okay, so the approach so far works great until it doesn't work, and this is because it is really strict about mixing static and dynamic computation, right? So here we have an example. So we have a function eval that takes some pointer to a node, right? And you can think of it as an AST node. So we know everything about this node at compile time. But here we get an error because the loop in this function f, it goes through all the nodes until the node returns a non-zero value. And since this condition is dynamic, the branch is also dynamic, and the fib functions in this loop header are also dynamic. All right, this follows from the rules of binding times, right? And that means that we have a contradiction here because the parameter to eval is of stage 0 as declared, but the argument is of stage 1, right? So how do we deal with that? Well, we added a built-in. So the problem was that this call it combined both the static and dynamic parts, right? So we evaluated both calls at once in one block and controlled by the same condition, right? But we can separate it into two parts, right? So we can have one loop that is very static, right? That goes through all the nodes and stores, and it only performs the call to the specializer, and it returns the function pointer to the next stage. Okay, so we can store these function pointers in a variadic array in C, and in the next loop we can call these pointers instead of the eval function. And this way, on this line, we can specialize eval to every node, right? And here we just call these function pointers, right? So one caveat: this doesn't work with the normal code gen because it requires a JIT, right? So this means that previously we could maintain the same code base for our interpreter and for the specializer, but now in some cases we have to diverge. We have to introduce a another like a function or two just for a specializer to deal with some issues, right? This is the residual code, right? So the first loop is completely unrolled, and the second is a normal loop. Yeah. So now we'll talk about some examples. So this is the base case, sort of. So we have some expression tree of operations, and we specialize it to some particular expression, right? And on the left we have a recursive function with the switch, right? And on the right we have a single basic block. Yeah. So, and the similar example with convolutions. So we have our 4 nested loops, and we can replace the 2 innermost loops with one basic block that just applies, that is very specialized to our kernel. Okay, so it only has like 9 operations. Okay, string formatting, similar. Yeah, so in these cases we have some improvement. So here, like in 3 or 4 times, or even like bigger than that. Yeah. Now I'm going to show some of the example with the dynamic control problem. So here we have a bytecode interpreter, and it has some instructions that operate on some register machine. Right? So we have some registers, we have some operations to load a value into a register, to add them, and so on. And all is good until we have this jump instruction, jump on a condition, right? And it exemplifies this dynamic control, because now this block branches either to the end of the like either to the loop header or to this block with this operation, right? And this jumps back to the header. So from this operation, we kind of have two static terminators that jump to the loop header, and we can have 2 because we have to pick one to move it to the specializer, right? So what happens is that nothing here gets in the control flow optimized, right? And we get only a modest improvement, right? But let's go back. So how can we deal with that? Let's apply our built-in. Right, so first we split it into 2 functions. Right, first function just returns the offset to the next instruction, right? And we have our dynamically controlled loop here. Okay, so let's apply our trick with the built-in. Right, so we have now the array of function pointers, and we call this built-in, right? And now on this line this loop is completely unrolled, and we specialize this eval instruction with respect to every instruction in our sequence of instructions, right? And then we call our function pointers in a loop, right? So this is an improvement over the interpreter, right? But it's nothing of an improvement over the original interpreter. It is slower, right? So let's go back again, right? So here is our test program, the Fibonacci program that takes, so, and the first four instructions are shown on the right. So this is the specialized code to each of these 4 instructions. And we may know that each of these instructions, aside from the last one, jumps to the next, right? And this is very inefficient because each of these instructions or functions are very like small, right? But we have lots of function calls between them that are indirect, right? So let's go back. We can change our function in C. We are staying in the interpreter land, right? So everything here can be run as an interpreter, aside from the drive function. So if we specialize that, we get this basic block. which I can call the basic block because it is actually a translation of the basic block of our bytecode program. Yeah, and we got an improvement over the original. Right, so we got 36 nanoseconds in our optimized version and 87 from before. Right, this is a toy example, but it shows like some of the features and some of the features of our interpreters that we have to deal with, and what we can and how can we deal with them in this way. Okay, so these are all toy examples. I want to apply this to some kind of real program, right? Some size, right? And there's also one thing that with annotations, because we have to annotate every function that our interpreter calls and that we want to specialize, right? Instead, what if we have some inference interprocedural that we can apply to propagate these annotations across functions? Okay, and yeah, we have only one front end for C. Like, it's very easy to write because it doesn't have to do anything. It just it has to translate these attributes down to IR, right? But I only have one front end to show, and yeah, that must be it. Yeah. Okay. Do you have any questions? Okay.
Are there any bounds on the increase in code size as the specializer runs?
In code size, yes, there is an increase. In code size, I didn't measure it, but yeah, there is an increase.
That's more, is there anything limiting the increase?
So the question is there something limiting the increase in code size? No. Currently, there is nothing like that. So the code size can explode significantly. Yeah, and this is a problem potentially. Yeah. Any other question? Okay.
Yeah. So I have a like a Game Boy emulator and like a brainfuck interpreter, like implemented exactly like how you had in that example. So theoretically, I could use llvm.mix to specialize the interpreter and wind up with like a much more specialized block of like for the eval routine.
Yeah. So the question is whether this can be applied to a brainfuck interpreter that is written in this way. Yes.
Or even like a Game Boy emulator
yeah.
or other kind of emulators.
I think so. Yes. Like, I'll be happy to help if there is anything, any problem with that. Right. I should note that this is all like a prototype, so it doesn't work like on all optimization levels and so on. So it doesn't handle like a debug info and stuff. But yeah, this is just a proof of concept of such a tool. Okay. Any other question? Okay.
You did say you plan to next look at real-world examples.
Yeah.
What do you think is a real-world example that requires the least amount of work to go from where you are now to improve a real-world example? And what do you think the hardest real-world examples might be?
Okay. The question is, what are the potential real-world examples that they can start from? And well, previously I have been working for a query compilation in databases, right? So this is kind of inspired by the domain. So I think I will start from some kind of small database engine or some query engine, and try to specialize that, right? Because they have this program that is a SQL query, and they have an interpreter that interprets this program. So it kind of a fit for this approach. Okay.
So, for example, I think Postgres now has some LLVM code generator built in. Does it make that better? Or?
Well,
I think it would be an alternative. I wrote that.
Okay.
I think it would be an alternative because we manually generate the IR and do the specialization by hand, basically.
Right.
But there is an interpreter that you could unroll with an input program in theory.
Yeah.
Yeah. So there is a Gene compiler in the latest Postgres version. Yeah. For expressions and for queries, even like some parts. And of course, this only works with compilers. So I'm sorry, with interpreters, right? So we can take the earlier interpreter that there was in Postgres, or there maybe still is, right? And we can work with that. And actually, like one of the earlier versions of this tool was specifically built for the Postgres. Yeah, but it was built differently. It wasn't it was a different tool, right? Any other question, right?
You mentioned in passing termination. What are the prerequisites on the program for your specializer to terminate?
It will terminate. So the question is, what are some prerequisites or conditions on the program that are needed for termination? And the answer is, if it passes the binding time analysis without errors, right? So then it will terminate, right? Because the analysis, it enforces a set of rules, right? And the termination is a condition on these rules, right? So as long as these rules hold true, then the specializer will terminate, right? But it is very possible to write annotations in such a way that they are inconsistent, right? So we can pass a dynamic argument to a function that takes an argument in an earlier stage, right? So it is possible to write this code, but it won't pass the checks in the analysis, right? And as soon as it passes, it will terminate then after that. Okay, any other question? Okay.
How does it relate to previous attempts of partial evaluation in llvm? I think there's something like LLPE.
Yeah, there is LL. So the question is, if this relates to previous attempts for partial evaluation in llvm, like LLPE. Yes, there is LLPE, which is built a little bit differently, very, very differently. It works without the analysis part, so we cannot. The difference, as I can describe it, is that the LLPE, it works in a single stage. It is an online partial evaluator, right? So we don't have the intermediate annotated representation to explore where what parts will be executed in which stage, right? And the second part is that as soon as LLP doesn't have memory annotations, and it is hard for them to add them because it kind of requires this compiler integration, right? And what this project has is it can annotate some types or some fields in some structs or some variables in such a way that we can partially evaluate loads and stores to these variables, right? And in general, LLP is more focused for input and output partial evaluations, also some files or some input that the program can take and be specialized to. And this is kind of more. It has a different focus. It is a focus more on interpreters that are not as standalone programs, but are parts of some other program. Yeah. That is, yeah, okay.
Have you done any analysis how much performance you gain by doing the specialization in multiple passes rather than in one combined pass?
Well, so the question is, what are specialization benefits of having multiple stages, right? And it all depends on application, right? So if we take this, for example, with query a compiler, right? If we take multiple parameters for one query, then it is profitable to specialize it multiple times, right? And each time we do it, we either pay this additional overhead if we don't have the previous stage, right, in between. So can maybe jump to the slide, right? So it only makes sense to add, for example, stage P1 here if the code that is returned from this stage will be executed more than once. If it is executed 1,000 times, then it is obviously more profitable to add this stage here. And likewise, for stage P0, it is only profitable to add this stage if this stage will be executed like many times, right? So with query processing, we can have like one query that is parameterized multiple times in some session or like some execution session, and then each query will then take multiple parameters from the database, and so it has this kind of structure, right? It all depends on application. In some applications, it doesn't make sense to split the stages because like they are not split in real life. Like you have one block of arguments that you pass at one point in time. Yeah.
Time's up, but if there are small questions for the speaker, I'm sure you can find him afterwards.
Okay.
Thank you very much.
Thank you.